Nobody has to like it. I did. I got mine.
Yeah, where's his one? Up there.
It's like. Remember some of the funny things? If you. No, it's not. I look at all stores.
All right, if you might turn to your books, we will be looking in the book here on page 260 is where we'll be. At some point along the way, page 260. So, today the plan is to do a little bit more with Newton's method for finding roots of a function, and then answer some questions in sample 2, and then give you some more time to work on both of those ideas, Newton's method and then some more in sample 2. So if we go back to what we were talking about yesterday, Newton's method is a method for finding where a function crosses the x-axis, which of course is a very important kind of thing because it's basically a way of solving any equation. Because any equation can be written so that you have 0 on one side, right? I mean, any equation, if you got x's over here equals x's over here, you can move everything over to one side, and then you have a function equals 0. Okay? So finding the roots, the zeros of a function is a really important thing to do. And then, of course, in calculus, we talk about how we always want to know where the derivative is equal to 0. Or possible inflection points are where the second derivative is equal to 0. So solving equation equals 0 is important to us just from that standpoint. But really, it can be used to solve any equation. Then we talked about how your calculators are programmed in this fashion to do the solve function, or partly to do the solve function. For example, we talked about the trig one, where we have to do the vertical bar and limit the domain. Well, that's basically what that does is helps give the solve function a guess, something to guess, right? If I tell it to look between 0 and 5, that helps it to look in that region. It's kind of like when we do Newton's method with our initial guess. All right, now, next week, there's probably no test or quiz, maybe the take-home one, but no real in-class quiz or test that we have where you'll have to do Newton's method. It's not on the midterm, not on the final, not on the AP test. Yeah, I just think it's an interesting topic, a little bit of a historical look, and it kind of shows us what happens with the calculators. And it's a good application of a derivative. It's just something they choose not to put on the AP test. So we do have a quiz next week that is what I call the no calculator quiz over chapter 4, which is the ideas of chapter 4. And so there will be some questions, or could be some questions on Newton's method, about the process of Newton's method and what's going on. So that's really what I want you to understand here. So this was the formula. Remember, this came from where? Where did this come from? Remember how we did it? Tangent line and what did I do with the tangent line equation? I pull up those notes, but I don't think I have. We set it equal to 0 and solved it for x. We took the y equals m times the parentheses x minus x point plus y point, and we set it equal to 0 and we solved it for x. In other words, what you're doing with Newton's method, let's just look at the picture here. We make an initial guess, we go up to the curve, we draw the tangent line, and we go down and we see where the tangent line crosses the x-axis. Where is a tangent line equal 0? Because solving a linear equation is much easier than solving a cubic or a sine or some of those other ones. So we took the tangent line equation, set it equal to 0, and solved it. That's where this little formula comes from. And then we repeat. And so we plug that point in, we do the tangent line, and we see where that crosses. And we repeat, and we repeat, and we repeat. And where it crosses gets closer and closer to where the curve crosses. That's what Newton's method does. So when we run this little formula here, those are the numbers we're finding, is where the tangent line is crossing subsequent tangent lines, where they are crossing the x-axis. And hopefully they're getting closer and closer to where the curve crosses the x-axis, and that's what we're looking for. All right, so we go to this problem that we were on yesterday. Isn't this where we were at? We were looking at this problem right here, this cubic. We want to know where that equals 0. So we do the derivative, and we use our little Newton's method formula right here. Now I told you could cheat a little bit, and you could use your calculator. And so what we did is we said you could define f of x to be that function, define g of x to be the derivative function, and then we could plug in this little formula. So what we were doing is I think we had stopped about right here, hadn't we, yesterday? So we made a guess that -1 might be a root. And we plugged -1 into here and we got this. Okay? Now we take that and we plug that in. So this would be like, this is where our first tangent line crosses. So we're going to plug that in, get a new tangent line, and see where that crosses. That's what this formula is doing. Okay, so that would look something like this. So we would type in one way to do it. Now Bailey was about to tell us of another way here. And so I want to get, why is it doing that? Okay, there we go. Oh, that's why it's doing it, because I got to choose. Okay. -1.25 minus, and then a fraction, and then f parentheses -1.25, and then g parentheses -1.25. And we got that. Is that what you were saying? Okay, and now what do we want to do? Plug that back in. So one way to do it would be to go up and grab that, and then go minus, and then a fraction, and then f parentheses, and then go up and grab that, and then g parentheses, and then, oh, whoops. I don't think it's going to let me grab that. How about if I copy? I know it's not going to. If I hit enter, then it sticks it in up there. So that's no good. We tried that last period, and that didn't work. So then somebody suggested copy and paste. So I could go Control C. Bailey, this is more work than I need to do, isn't it? Okay, but let's try it. So we're going to go Control C, and then we're going to arrow down, and then we're going to go Control V. Of course, 100 years ago, they'd really wonder why we're complaining about having to do this much work, right? And we get that. Now, what do you notice? What are we looking for? Yeah, we're looking for these two to be the same, right? So what's happening is these tangent lines are crossing, and they're crossing at almost the same place, which is probably right where the function's crossing. And we're looking, we said 3 decimal places, right? And that's a 4, that's a 3, so we didn't quite get it. So we're going to do it again. So we're going to arrow up to that, minus, and then we're going to do that, f parentheses. Now what we're doing is we're plugging that into f, and down here this is f prime. I mean, I called it g, but it's really f prime. So I'm going to copy that, and I'm going to paste it in there. Control V is paste, and we'll look what we got. Looks pretty good, right? 2, 1, 3, 4, 1, 2, 1, 3, 4, 1. So it looks like we're good out to about 5 places, right? And then if I do it again, I think they all agree. I don't know if you did it one more time. Okay, so Bailey, now I think I know where you were going yesterday. Tell me what you were going to do with this.
You define another function which said that h of x equals x over g of x.
Okay. Define h of x equals f of x divided by g of x. Okay. Go ahead.
Typing in numbers, you capture the when you're doing it, and you're going to minus h of x with
That one.
yeah.
So I could go this. Oh, I should have done Control Enter. I like decimals better. And then I could grab this minus h of that, like that. And then grab that minus h of that. Right? Okay?
Can you
x minus f of x over g of x.
What do you think? Say that again now. Define.
Define
Let's call it M.
m of x, x minus f of x over g of x, h of x.
Oh yeah, just do H of X, right? Now, since we'd called it that. And then go negative, so, and then, whoops, M of negative 1, and then M of that, and then M of that, right? That's all good stuff. There's even a better way. Yeah, what I'm about to show you, I called the super duper shortcut. The one I showed you might call the shortcut, where we can use our calculators, literally. And then I think what Bailey said would be like a super shortcut, and this, I guess, is even more of a shortcut. So, really super shortcut. And then there's another one that's even a little better. And then, of course, the really super mega shortcut is just solve. You type in solve. And then that's doing all it for you. But here's the one that I was thinking of is what we always do in Newton's method is we take our previous answer and we plug it in. Right? We take our previous answer and plug it into the function. Now, in all these examples, we were going up and grabbing our previous answer. There's a key on your calculator that will automatically get the previous answer. See the negative sign? See the ANS there? That's like a variable that stores automatically the previous answer. So, but the one thing you got to do with that one is you've got to do the first one, or you've got to have a previous answer in there. So what you can do is what we call seed the calculator. So what did we start with? -1?
Yeah.
So in this, I would just type in, darn it, -1 and just hit enter. Now -1 is my previous answer. So -1 is stored in this variable called ANS. And so what you can do then is go control and the negative and do answer minus, and then, well, we could do M, but I'm going to say we hadn't done that. And I can do F of answer, and you can do this with the H and those things too. And then G of answer. You see what I'm saying? Now, watch what happens. When I hit control enter, this is really cool. When I hit control enter, I get that. Now, that is stored in the previous answer. What could I do right now? If I just hit enter, remember, anytime you just hit enter, it just repeats the previous calculation you just did. So if I just hit enter right now, it will repeat the previous calculation. But remember, the previous calculation used answer, which was the previous answer. So what it'll do is it'll do my last calculation with the last answer already plugged in.
Witchcraft.
So now all I have to do is hit enter. I just keep hitting enter, and it's got it.
Witchcraft.
Okay. Now let's imagine here. Let's imagine that I wanted. What's nice about this is it lets you do some guess and check stuff, some cool what if things. Now again, I told you yesterday that when I was in calculus, we didn't learn about Newton's method. Well, we didn't have the power of this technology, so the hand calculations were too. It was just too much. We just didn't do it. Now, 100 years ago, they had no choice. And so scientists or whatever that needed to do something with this, they just had to do these hand calculations. But, we just didn't do it. But now, it's a more interesting topic now because we can talk about how, hey, this is how your calculators are doing it. Somebody programmed this kind of thing into the calculator to come up with these. There's a tolerance setting in your calculator. So if it's set to like 12 decimal places or whatever, then what the calculator does when you do a solve is it runs through this until it does just a loop. For those of you that were in programming, it just does a loop until it gets to the 12 digits of accuracy, or whatever digits you set as the tolerance, okay? And so that's how that's working. So it's an interesting topic nowadays because of the technology we have. But we don't have to run through it. Like you said, like Alex said, we can just do the solve. But it's kind of nice to know, in this case, how that works. So let's say we made a bad guess. Okay, -1's pretty close to the actual root, right? So let's say we guessed like 6. So let's just go 6 in the inner. And now we can just do answer minus, and then f of answer over g of answer. And now I can hit enter. Oops, that gave me a fraction. Let me get a decimal. Enter, and I get 2.5. And then I hit enter. I get 1.4, and then 0.405, and then -1.9, -1.4, -1.23, and eventually here it comes, and then we eventually get back to that root. And so you can picture this thing I was showing you yesterday, where you've got these tangent lines, and what happened is we picked the tangent line way over here. It gave us that first answer, which was out here, and then the next one here, and the next one here, and the next one here, and pretty soon it was boom, 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 and it was giving us the root. Fine. Okay? So it's kind of cool where you can see those sort of things. And in your book assignment, you're going to get a chance to do that a little bit with some different what ifs, and so you'll get to use this kind of this answer method, this super duper shortcut on one of your homework problems. Okay? All right. So that's kind of a cool thing to see. But you're not going to have, like I say, on the test or quiz where you have to know how many roots it has without being able to look at a graph or have to go through all this. Okay? Just I want you to understand the process, and I want you to and what it's doing, and how it's doing it, what it's finding. But there is a little bit on the homework here that I want to do. So let's do this problem next. What I want to do is, and I want you to write this down because you're going to, one of your homework problems you're going to have to do like this. So what we're going to do is we're going to make kind of a table. Like this. And so one of the homework problems you're going to use what I'll just call the table method. One of the homework problems you'll get to do the super duper shortcut on the calculator. But the table is going to be informative as well. The table is going to tell us some things also about what's going on. So while you're writing that down, I'll tell you a little bit about the problem we're going to do. Another place where something like Newton's method was used was in calculating square root values. Okay? If you go back to the math books of my era, when I was your age, the math books would always have tables in the back of them. They'd be logarithm tables, there'd be sine and cosine tables, there'd be square root tables, maybe cube root tables, okay? And, you know, the first calculators that came out that were widely available only did 4 functions. They add, subtract, multiply, divide. So if you needed a square root, it wasn't on there. If you needed the sine of something, it wasn't on there. Now, eventually then they came out with fancier calculators, so they called them scientific calculators. A scientific calculator is one that has sine, cosine, square root, more of those things on it. And so when I was in high school, those were available. You could get one for $30, okay? Kind of like the TI-30s and so forth of today. They were a little bigger, bulkier, you know, so we're talking 1980, somewhere in there. But it wasn't too long or too much before that where they were over $100. I mean, in the early 70s, rarely, mid-70s, rarely did anybody, you know, have a calculator. They were just too expensive, so in high school you didn't use them very much. So gradually this became phased out. You look in the back of the books now, you don't see square root tables and trig tables. Okay, but if you wanted to know the sine of 40 degrees, up until the mid-70s, you went to the back of the book. There was a column for sine, a column for cosine, a column for tangent, and you looked up, well, not even tangent because you just do sine divided by cosine. And then you went down the side and you found 40 degrees, and you looked over and there was a sine of 40 degrees. And then you used that in your calculation if you needed. Okay, well, same thing with square root. If you needed to know the square root of 2, you went to the square root table and you looked it up. Just think about it. How else would you do square root? When I did my first practice teaching, not my full student teaching, but the first time I went into the classroom and helped teach class was about 1984, and it was in a Lincoln middle school. Actually, we called them junior highs back then. And they were working on square roots. It was an 8th grade class. They were working on square roots. And I actually taught a lesson in this. So let's say we were trying to find the square root of 2. The 8th grade book back in that time talked about the divide and average method. Here's how the divide and average method work. What are you looking for when you're looking for the square root of 2? Two numbers that are the same, right? Yeah. Multiply together, right? So what would be a guess, fairly close, of a number that would multiply to give you 2 times itself? And you probably already know what it is, but you know, it's cheating a little bit, but it's bigger than 1. Because 1 times 1 is 1, 2 times 2 is 4. So it's got to be between 1 and 2, right? So let's say it's 1.5. So let's say our guess is 1.5. So here's what this was called, the divide and average method. So we would take 1.5 and we would divide it into 2. So I had these 8th graders all sitting around doing long division, right? We were all, you know, back in the day, we did a lot of that. And so now we're going to divide this. So we got to move that over there. When's the last time you guys did long division?
Last year.
Has it been? Not too long. Some of you have been real long. Okay? So we move the decimal over 1, we put it up there. Right? 15 goes into 20 one time. 15. 15 into 50 3 times. 45. 50. Okay, it's going to be 3 repeating. Okay, now what were we hoping would come out there?
The same number.
1.5. Right? We were hoping 1.5 would come out, but it didn't. So it's called the divide and average method. So what we would do is we would now average those 2. Now we could make it easy ourselves, call this 1.3, 1.5, so an average is 1.4. So we'd do it again. So they would take 1.4 into 2. So we'd move the decimal over, go up, 14 into 20 goes 1 time. 14 into 60 goes 4 times, is 56. 14 into 40 goes 2 times, 28. 14 into 120 goes 8 times. 8 times 4 is 32. I know that because we did this last block. 8 times 1 is 8, plus 3, that's 11. Right? Remainder 8. Okay, so now, again, I was hoping to get 1.4, but I can tell I'm getting closer. Right? So 1.4 and 1.428, so an average of that would be 1.414. And so then I would do that. Now that's going to start to get really ugly now, because now I got to move that 3 places, so I got to go 14 into 2,000, right? But it depends how accurate you want to be, right? So if we want 3 decimal places, 4 decimal places, whatever, we'd have to do more division. But that was called the divide and average method, and that's how you found square roots. Okay? So we, you know, or we would, you know, then we were glad so we were real happy when we could look it up in the table. If the teacher said, "Oh, just look it up in the table." That's good. I don't have to work it out, right? Now you can just type it in, square root of 2. You got it. So here's what we're going to do, though. We're going to do Newton's method to find the square root of 2. Okay? Now, I don't know that it's necessarily easier than the divide and average method, although that divide method, depending how far you want to go, wasn't real easy. But this is just going to be another way that we can find square root of 2. So what do we need? Well, remember what Newton's method gives us is the 0. It gives us where the function crosses the x-axis. So what I need is some function that would cross the x-axis at square root of 2. Anybody think of one? What would be a function that would cross the x-axis at square root of 2? Or what we're really saying is we want a function whose answer is square root of 2, right? When we set it equal to 0. What would one be? There'd be a lot of them, but I'm not going to tell you. You'll stand here all day. I'll stand here all day. You guys come over. Simpler than that. There you go. X squared minus 2. Wouldn't that be a simple one? Right? If you set that equal to 0, add 2 to the other side, do the square root, you would get plus or minus square root of 2, right? Think of that as a graph. That's a parabola shifted down 2. So it's going to cross the x-axis twice. Negative square root of 2 and positive square root of 2, right? So that function right there, if we do Newton's method to that, we should get square root of 2 out, right? So let's do it. So we need f prime, and that would be 2x. So the calculations won't be real bad here. And the nice thing about the calculations is the calculations are all multiplication and subtraction and not division. So if you had your choice, wouldn't you rather do multiplication than division? If you were working out by hand, you would, I think, right? And so when we do Newton's method, you might say, well, this was, and I'm going to let you cheat and use your calculators here, okay? So go ahead and get your calculators out and have them ready to go. But if you were working it by hand, this might be better than the divide and average because the divide and average has to divide, and that gets to be kind of tough. But with this, it's just straight multiplication. All right, so let's start with a guess. Again, we know it's like 1.4 or something, whatever, but let's just start with a guess of 1. Okay, so let's start with a guess of 1. So that goes in the first column. So the next thing we need is f of 1. Okay, what's that? 1 squared minus 2, that's negative 1. And then we need f prime of 1, and that is 2. And then we need to divide those. So that'd be negative 0.5. Decimals are probably better than fractions here. So let's go negative 0.5. F divided by f prime. And then the last step would be take your original minus that fraction. So this column is kind of like the H column that Bailey had defined. So 1 minus negative 0.5. 1.5. So then that becomes our next guess. So that becomes the next row of the table. Okay, now here's where we can use our calculator. So now we would plug 1.5 into here. Well, it's not that hard. Again, if you were working this by hand, 1.5 times 1.5 is not that hard to do. And then take away 2. 0.25. Okay, and then f prime of 1.5 is 3. And again, if you want to, when you're doing the table, you can define f to be x squared minus 2. You can define g to be 2x, and then just be plugging these into f and g if you want to do that, right? That might shorten it a little bit here. These functions are pretty short anyway. Okay, what's f divided by f prime? 0.083 repeated. Okay, and then finally 1.5 minus that. 4.1. It's like 6 repeating. Okay. Now at some point we're going to want to write down more decimals. So when we get to this next one, we're going to want to write more decimals. But the nice thing with your calculator is you're keeping all those decimals. So it's a lot easier. You know, if you're doing this by hand and keeping those decimals, it might have been better to do fractions for longer if I was really doing these by hand, right? And then I could divide those out. But if I have the decimals, I'd want to keep quite a few of them because the accuracy is what we're after here. All right, so this is 1.416 repeated. All right, what's f of that? 2. It should just be 0.00. Okay, I lost you. 2 zeros and then what? That doesn't sound. Okay, all right. Yeah, I was going to say I thought it was 6 something. 6, 9, what is it? 6? Yeah, now again, it's good to go up and grab that other answer, right, so we get all the decimals. Don't type in a rounded value because then that throws us off. Okay, what about f prime? 2.83 repeated. Okay, and then this column, f divided by f prime. How many zeros? 1? No. Yeah, I think it's 0, 0, 2, 4, 5. So that'd be this number, Brandon, be this number, go up and grab this number, and then divide by that number. Okay, and then finally you take the 1.416 repeating minus this number, and then give me quite a few decimal places on this 414 256. Okay, that's good. 1.4142156. Okay. Now, what do we notice so far? How many decimal places we got? We got 2 that are in agreement right now, right? We got 2 that are in agreement here. Okay. All right. So there's our next one, 1.4142156. Okay. But again, we're going to use all those. Let's do one more row. I think one more row is going to get it for us. Okay. So that one squared minus 2 are plugged into the f function. Now it gives you scientific notation, right? Yeah. Okay. So what's it give you? 10 to the negative 6. So that'd be 5 zeros. And then what? 6007. Something like that. So that'd be 5 zeros. 1, 2, 3, 4, 5, 6. Yeah, 10 to the negative 6. Okay. And then what about the f prime column? .828. Okay. And then this column, when we divide those, again, it gives you a scientific notation. 5 zeros again. And then what? Okay. And then finally, we take this number here and we subtract that number there. Okay. All right. Now, how many decimals of agreement do we have there? We got 5 of them, right? And so we feel confident that our answer is accurate here out to 5 places. So we feel good about square root of 2. Now, that's not bad. If you think about how long divide and average would have taken, and it's division, whereas all we would have had here is multiplication. Like if we were doing this by hand, we'd have had to take this number and square it. So that would have been some multiplication, which would have been a lot of fun, but I still think multiplication is better than division. And you'd add some subtraction, and that's about it, okay? Now, the reason of going through this stuff is the table, I think, really gives you some interesting information about what's happening here. And I want to combine this with the picture. I want to combine this with the idea of Newton's method. Every time we do one of these, it's like a new tangent line, right? Crossing the x-axis at a new spot. Hopefully, the spot getting closer and closer to where the curve crosses the x-axis. So when we go to this table, let's think about this. Number one, this column. What's this column doing? Getting close to 0. Why? That's what. Thank you, Melissa. That's what we want, right? We're trying to find the 0 of the function. We want to know when this function has an output of 0. So absolutely, this better be getting close to 0. That's what we want. That's the whole point of Newton's method, is to get our output of f to be 0. Okay, so that's a good thing. So we can see that's good that that's happening. Now this column isn't as big a deal. What is this column giving us? Slope of what? The tangent line, right? That tangent line that is going down and hitting the x-axis, that's just the slope of that line. Not really that important of a number. Could be steep, could be shallow, doesn't really matter. Probably not going to be very shallow, but it actually depends what the curve's doing. If the curve's coming through and hitting the x-axis really shallow, then our tangent line's going to be really shallow. If it's coming down and hitting it really steep, the tangent line's going to be really steep. So, to be honest, this number's not that big a deal. Okay? Now, this is a really, really important number. This fraction here. Now, it doesn't surprise us that it's 0. They're getting close to 0, because what is it? It's this divided by this. And so this is getting really close to 0. So if you take a really small number close to 0 divided by some other number, you're going to get a really small number close to 0. So that doesn't surprise us, but there's something more important here. How many digits of accuracy did we say we had on this line? No, right here. Well, after we get to the next line, we can tell we have 5. But really, from this line to this line, we know we have how many decimal accuracy? 2. 2 places agree. So we know this number here has 2 digits of accuracy. Now, it turns out it has more. We don't know that till the next time around. But this time, we know that's 2. Now, look at that number. It's got 2 zeros in it. Is that coincidence?
No, probably not.
How many decimal places accuracy does this one have?
5.
Think about what you do. You take your previous number and you subtract this. You take this number and you subtract this, which would be this number, right? So you're taking this number, subtract this. What happens when you subtract 0? Nothing. Doesn't change. So when you have zeros in these 2 decimal places, when you subtract from this, those 2 numbers are going to stay the same. Which is what we're saying. That's the accuracy. So when we see this, so as soon as we look at this column, we can tell how many decimal places of accuracy we have just by how many zeros are there. Okay, so that's kind of interesting too. So I think when you break it down and you look at it in this way, you really can see some things about the process and the method and what's going on. All right, so on your homework today, there's going to be 3 problems, and there's going to be one where you kind of have to somehow explain. They give you a graph, and you're going to picture, if I did Newton's method to this, what would happen. So it's just kind of an explain problem. You're going to have one problem where you're going to do a table, okay? And then you're going to have, so it'll be about like that. And then there's going to be a problem where you do that super duper shortcut with the answer thing. And it's going to have you try some things. It's got multiple parts, and you're going to try, what happens if you try this initial guess? So you'll get in there and do it and see what happens. And then what if you try this initial guess and see what happens? So now, if you look at page 260, we talked a little bit yesterday about some of the weird things that can happen. So if I take a look at one, and I'll just show you this again, and I think that's what's going to happen on the one where you have the super duper shortcut. You're going to see some things going on, and you're going to have to explain what's happening. So one of the things we talked about is cycling, which is actually over on page 261. So if you pick your initial condition here, takes you to there, next tangent line takes you back to there, and you just end up going back and forth. That's a bad thing, right? That's called cycling. Now, they mentioned something called the butterfly effect in there, which kind of gets its name from, they say, you know, butterfly flaps its wings in Europe, causes a hurricane in Florida. You know, the ripple, well, no. Well, but the idea is small changes. It's actually one of the fundamental principles of chaos theory, is that sensitivity to initial conditions, small changes can have large effects. It's kind of like the old throw the pebble in the water, right? And then the ripples, right, go out and so forth. So it's that kind of idea. And this also shows that. In other words, if I was, let's say I was just here at 1, just to pick a number, and it caused me to cycle back and forth. By just changing this number to 1.000001, I wouldn't get that. By just changing that a tiny little bit would cause this blue tangent line to move ever so slightly, barely, but you couldn't even probably tell. But if I move this over just a hair, this blue line would come down a little steeper, causing it to hit at a different place here, causing this green line to go to a different spot, and then on and on and on. But what would happen is big change, that little tiny change would get magnified with each step. Okay? With each step. So it's kind of like if somebody pointed you at a spot that was 3 miles away, and you blindfolded you and just said start walking. What are the chances that you hit that spot? Right? And if you just turn just a teeny bit and then walk, you know, it might make a difference in this room. If I start walking here and then turn a little bit and start walking there, I end up at about the same place. But if I do that over 2 miles, what happens? I could be a long ways away. Little tiny changes that expand and get bigger over time. So it's kind of the same thing here. The other thing that you look at here on this scenario is if I move this a little bit, what if I have this up near the peak? You know, it's going to shoot way out there. Now, of course, you can't have it right at the peak. Think of the formula. It's F over F prime. If you're right at the peak, the slope is what? 0. Then you'd be divided by 0, and then the formula falls apart anyway. Right? So you couldn't do it. But if you have a shallow tangent like this, it's going to shoot you way out here, which means it'll take you a whole bunch of iterations to get back to find a root. So that's another thing to keep in mind. But now, this is the other one I want to show you. And this is going to happen to you on your homework a little bit too. I want you to look at where I have this one here. This blue tangent line hits right there, which causes it to hit just on this side of the minimum. which then shoots my line off this way. And if I kept repeating this, I would probably come in here and find this root right here. But if I change that initial guess just a tiny bit, barely moved it at all, this blue tangent line hardly moved. It was over here, now it's here. But that causes me to hit this curve on this side of the minimum, which shoots my tangent line over here. And now if I kept going, I would probably find that root. You know what I mean? So, you know, we just did an example where we tried 1 and we ended up at 1.4. You know, we tried numbers pretty close to the root and we ended up at that root. Sometimes you can start near one root, find a whole different root. Okay? And there's no real good way of telling you what's going to happen, but it's just understanding what did happen and what are some of the things that can happen with that. Okay? So, not going to make you get into that in any detail or anything about what's going on, what just happened, but just understand that those are some things that can happen with this idea. And that's another reason this Newton's method has kind of come back into, you know, into vogue, I guess you might say, or you know, being studied a little bit, is because of things like the chaos theory and those kind of things, and the stuff, some of the stuff that we can look at with technology. Okay. Let's take a look at your sample 2. So that's, I'll give you the assignment here in a little bit on the book stuff, but get your sample 2 packet. Let's take a little bit of time to do a few of those. You know, remember the midterms probably in another week to 10 days. And we talked about the scale a little bit. You know, to be honest, somebody was asking about, you know, the grades. The midterm, it's 2 days, I get that. The final's like 4 days, but those aren't really tests to fear that much. I mean, you definitely want to work hard and practice for them, and they're hard. But as far as your final grade in the grade book, the class average is almost always higher on the final and on the midterm than any of our other quizzes because of the scale. Okay? I mean, that last quiz, the class average was 70.
We should scale that.
Something like that. You know, this, I wouldn't be surprised if the midterm doesn't have a class average closer to 80 or high. Okay? So, you know, now you still have to do the work. You still have to put in the work on these packets. And to be honest, the average of the final is usually better than the midterm. And that's because usually the midterm, it seems like maybe more people just don't put as much time into that. We do have more class time to spend on it when we get to the final, so that's probably one of the reasons. But I think some people also say, you know, I should probably have spent more time in the packets than I did on the midterm. So something to think about. Okay, any where do you want to go? We can do a few of these. Anyone? Bailey?
8.
Yeah. 8? Yeah, I know. I hit my button too many times. All right. The function has a horizontal tangent and a point of inflection for the same value of x. What must be the value of b? Okay, this is kind of a chart kind of problem. Horizontal tangent means what? F prime is 0. Inflection point typically means F double prime is 0. Now we could get into things with F double prime undefined and that kind of stuff, but this is a nice polynomial function, so nothing's going to be undefined or anything like that. So it's going to be probably when F prime is 0 and when F double prime is 0. So what's going to happen is you notice there's a b in there, so you're probably going to have this unknown. So if we can set up 2 equations, we can a lot of times find that value. Okay, so we're going to start with the derivative, which would be 4x cubed plus 2bx plus 8 equals 0. Okay, that's one fact, and it's at the same value of x now. Okay, and then we also want f double prime, which would be 12x squared plus 2b. We want that to equal 0. Right? So what we could do is solve this one for x, and that's where this thing will have an inflection point. So 12x squared equals negative 2b. X squared equals what? Negative 1/6 b. And x would be the square root of that. Now it'll be plus or minus. And so that tells us b has probably got to be, I mean, I can tell right away that b is going to have to be negative, isn't it? So I've already narrowed it down to one of those two. So now you've got a couple choices. One thing we could do is go through the process here of, you know, the normal kind of process of what we would do with something like this. Or we could cheat a little bit because it's a multiple choice. I could take and plug these in for B and try them and see what happens. So, and this is a no calculator one, right? So my original idea was to come and put this back into here. Okay, and then I would have this just in terms of B, but that looks like that's going to be kind of, I feel like I'm missing something here, but maybe not. I don't think so. Okay, let's substitute that in. So we get 4, then this thing cubed. I'm not going to worry about the plus or minus right now. That'll go better. I'm hoping something nice happens. Actually, I think it's good. And then plus 8 equals 0. So now what is this? If you cube a square root, what happens? Well, in other words, like if you had square root of x and then you cubed it, that'd be like square root of x times square root of x would just be x, and then another square root of x would be something like that. So this is going to be just 4 times plus or minus 1/6 b, and then a square root of negative 1/6 b, plus, and then this is 2b, yeah, I'm missing something here.
The numbers looked a lot nicer.
Yep.
I just took the F double kind of thing instead of doing 0 and then solved for B instead of F. No, that's what I was gonna say. It seemed a lot easier to solve.
Oh
for B
yeah,
instead of
why
X.
would I want to square root something?
Yeah.
Yeah, I'll be honest. Yeah, well, I'll guarantee you if I was hoping, because a lot of times with these square root things, when you get into them, especially in the no calculator part, a lot of times something nice kind of happens. You know, like you square it, you plug it back in, you square it, the square root goes away, and there you go. We also get into some number line ones. We haven't seen one yet, but we also sometimes get into some number line problems, some chart stuff, where we have like some square roots in them, and we have to deal with those. So you can't, when you get into a square root, you know, you wouldn't always just say, well, it can't be this. It's got to be easier than this, because sometimes it does. But this one, the farther I got, the messier it got. Now sometimes when you do that though, the farther you get, the messier there's something you missed that was pretty basic that you probably should have seen. That's why I kept thinking I missed something here, and it turns out I did. Yeah, I should have just solved for B here. And that would have been nicer, because really all I have is 2 equations, 2 unknowns, right? I've got x and I've got b, and so what you need to solve one, substitute for the other. There's no rule says you have to substitute, you have to solve for x and substitute. You can solve for b and substitute. So that's a great idea. So we get b equals negative 6x squared, and then put that back into there. So now we get 4x cubed, minus 12x cubed plus 8 equals 0, which is negative 8x cubed plus 8 equals 0, so negative 8x cubed equals negative 8, x cubed equals negative 1, and so x would equal negative 1, so it's, oops, I didn't circle that. So we end up with B. But again, what would not have been, oh, that's positive. Positive. So X is 1. There you go. Okay? But that's, wait, that's still not what we want though.
No.
Time out, time out. Because what is 1? Negative 8 divided by negative 8, that's X. We want B, so we come back over here and we get negative 6. Okay? Now I'd like to say I was right when I circled it before, but that's not why I circled it, because that was the answer. I was going to say that I think what I had done at a certain point was plug these two in, right? Because right when we got to here, right, we knew B had to be negative, right? Remember what I said earlier? When we got to this point here, we knew B had to be negative because 12x squared is going to be positive. So, and even looking here, the only way this is going to equal 0, B is negative. Okay? So we knew B was going to have to be negative. So you have those two choices. A lot of times, if you can eliminate down to 1 or 2 in a multiple choice, it's not a bad idea to just plug those in. So you could have taken right here, taken your negative 6 and plugged it in for B, and you could put your negative 6 right here for B, and then went from there. And then put negative 1 in for B, and then see which one worked. Okay, so once I knew B was negative, that's probably the way I would have went on that one, just because obviously this was getting me in trouble here. Yeah.
I approached it a different way, and it got really messy really fast as well.
Yes.
Same X value. Now it got really messy, and I didn't know where to go from there, so I just kind of stopped. I was going to ask you about it.
So you got an X of 1.
What I did was I put my F prime equation and my F double prime equation equal to each other.
Which is the same thing, right? Since these two equal 0, you can put them equal to each other. But see, that's what, oh, you mean at the beginning you did that.
Like right
And then you solve for
X.
X.
Like I think I solved for B, and I put that into it.
What'd you get for the B? You should have got that. But you're not sure if you did. Yeah. No, that was another thing I thought about doing. That's something you can do. I mean, since these both equal 0, we did 2 equations, 2 unknowns, where we solved one, substituted the other, which is fine. The other thing to do is to set them equal to each other, solve for one of the variables, and then you got to plug it back into one of them. That's the key. So if you did get X as 1, you're good. Then all you had to do was plug it back into this one or this one. It'd be easier to do this one. Because look, if you plug a 1 into this one right here, right, then you get negative 6. So no, that's the idea. The idea is that those two have to be equal. Horizontal tangent and a point of inflection, the first derivative and second derivative both have to equal 0. Okay? All right, good one. What else? Yeah, Cody.
Do you have any questions about the answers or what constants at the end?
Okay, so help me out here. What did you do? What approach did you take? They give me the velocity.
I did like the
Antiderivative would be fine. That's the position. Oh, it's moving along the y-axis. This is a technicality, but I'll call it y. Go ahead. Well, right. Here's the key. When you do an antiderivative, you need the plus c. You need the plus c. And then you need some initial condition. So the particle moves up until it reaches the origin. So that tells you that the particle at some point is going to have an output of 0. But what we don't know is the time that it's going to be there. Right. Well, I would agree that y. Okay, so what we have is the y-axis here. We got a particle moving up and down. It says it moves upward until it reaches the origin, so it's going up, and then it's coming back down. Right? We don't know where it starts. We do know at time 0 would have to be negative. So yeah, from a multiple choice situation, you could plug a 0 into these, and you know you've got to get a negative answer, right? Because it says it moves upward, so we know it starts in a negative position. So if you put 0 into this, you get negative 16, so that's a possibility. Put 0 into this, you get 16, so that's no good. Eliminate it. Put a 0 into this, you get negative 16, so that's no good. Although, but look, it's got 2t squared, we know it's gotta have, right? So maybe you can eliminate that. This one you put in 0, you get 0. This one you put in 0, you get 0. So maybe by process of elimination, we get this one right there. Is that the right answer? Is that what everybody's getting? Because you can tell this one can't be it because of its antiderivative. So that's not a bad way to think through that one. Now here's how we would actually possibly work this out. Is we would have to figure out, well, I'm not even sure we have enough information.
Just set the velocity equal to 0.
Oh, yeah.
Well, if we set the velocity equal to 0, since it turns around, that's the key, right? It turns around when it's at the origin. So what happens when it turns around? Velocity is 0. So if we set the velocity equal to 0, we get t equals 4, right? So at 4 is when this thing turns around, which happens to be when it's at the origin, because that's what they told us. So we do have an initial condition. We know that at time 4, it has an output of 0. So we could do this. We could put our y value of 0, and we could put our 4 right in here, and we would get this. But I like what you guys were saying. I think that's a fine way to come up with that one as well. And so we get this, and so we get 0 equals 16 plus c. We get c equals negative 16. So that's how you can tell for sure that it's that. Okay? And that's a differential equation is what that is, right? This is a derivative, the velocity, and it's an initial condition. But you did have to do a little work to get the initial condition. That's the key there. All right. Let's see. One more. Keep. 13. This is an implicit differentiation. Okay? Now, we didn't really get into any in the calculator section, in the next section, so if you got some of those want to come in, we'll have another day here where we'll maybe be able to do some more. But okay, so we do the derivative of x is 1. Derivative of y prime. Got it? Product rule. So 1y plus xy prime here. Yeah, so it's just pretty much a differential equation. Or excuse me, a implicit differentiation. So now you want to get the y primes together. So if I subtracted these over here I'd have y minus 1. Take out a y prime, I get 1 minus x. Now the only thing about this is sometimes then it's backwards. Let me see if I got lucky. Did I get lucky? I did not. Mine doesn't match any of those. Which one is it though? It's C. Because look what I can do. If I take a negative out of the top here, that would be 1 minus y. If I take a negative out of the bottom, that'd be x minus 1. And then a negative cancel negative, right? So 1 minus y over x minus 1 is the same as what I had. Now, I'd have got that. I say I got lucky. If I would have moved the y primes over to this side, then I would have got C. My answer would have come out just like C. Theirs was. Okay? All right, one more. We can do one more. That was a quick one. Anything in the calculator one? Well, yeah, they're all easy once you see kind of what this, you know what I mean? And that's the way the midterm is. I mean, well, not they're all easy, but it's just a matter. That's why we do 4 packets. Not so I can kill trees, not for busy work. It's because the more often you see them, see, next time, Keaton, you see that one, you're going to go, oh, yeah, right, implicit differentiation, right? So the more often we see these, the better off we'll be. 23. Oh yeah, this is, okay, related rate like we have here. This is a cube. So volume of a cube is s cubed. In terms of the edge, what is the rate of change of the volume? So we're looking for v prime. The edge is increasing at this, so that would be s prime. Right? So v prime would equal 3s squared s prime. Right? So v prime would equal 3 times 0.05 squared No. Plugged it the wrong place. 3s squared times s prime 0.05. 3 times 0.05 is 0.15 s squared. Right? So v prime is 0.15 s squared. In other words, normally in a related rate problem, they would tell us what rate is the volume of the cube when the edge is 6 centimeters. And then we'd have plugged the 6 in for x. But they did, but all their answers had s's in them, so that's fine. That's good. Cody, make sense?
Yeah.
Yeah. So a little bit different than ones we've seen, but it's always nice to look at the answers. You're doing this, you're thinking, geez, I should have something plug in for s, but then you look here and say, oh no, the answer should have an s in it, so I'm good. All right, I want to give you some work time here today, so let's, and if you've got some questions in the packet, that's fine. Your homework is, and I think it's on the assignment sheet, section 4.6, starts on page 261. Okay, this is the Newton's method stuff. Now, let me tell you real quickly about these Newton's methods problems. I think you'll understand as you read them, but let me be real clear about what I want. Number 3, they give you a picture and they say, if you started Newton's method at this point, what would happen, kind of a thing. So you might want to sketch a picture, but it's basically an explain kind of problem. You don't have to do any calculations. They don't even give you a function to work with. They just give you a picture. So that's just more of an explain. 5 is a table. They're going to say, look at a, here's a function. Find the root that's between 0 and 1. So pick a number in between 0 and 1 as your guess and do the table, like we did for square root of 2. Okay? And then 15 is the super duper shortcut with the answer key. Okay, on your calculator. Not the one where you just do the solve. Don't do that. But what it does there is it says, it first says find the 3 roots. So go ahead and cheat a little bit. Draw the graph if you want. Draw the graph. See where it crosses the 3 different times so you can pick numbers close and then do your super duper shortcut with it to find the 3 roots. That's what I would prefer you do. Now, how am I going to know if you did the solve or not? I won't. But, okay. But do that thing with the answer key is what I'd like you to do. Because you need it when you go to parts B and C. In part B, then, it says something like, try 2 as your initial guess. So you put that into your super duper shortcut and see what happens. And then C is they say, now try 1.39. Something weird's happening. Explain what's happening. And so you try that, okay? So that's what I want you to do with the Newton's method there. Then the rest of the assignment is more sample 2. I mean, for today, I really was talking about the second multiple choice section. So now we're talking about we should get into the free response. Don't get behind on this, because this is a big part of our homework right now. There'll be a couple days coming up here where we got plenty of book homework. You won't have much time to work in the packet, probably. So don't get behind right now in the packet. This is yesterday, today. These are days we should be doing a lot of packet stuff. So we should try to get through maybe all of sample 2. Now, you're not going to get them all done, and you'll have questions on some for sure. But try to get through as much of that as you can. All right, rest of the time is work time.
Mr. Clark,
Yeah.